Hello everyone, welcome to the present class where we will discuss a very important concept, and this is important because in thermodynamics probably we have learned the basic cycles in our earlier courses of thermodynamics. Now, we will see that how the basic cycles can be combined and how we can have a better conversion of energy, better utilization of energy, which we are taking from a source which is available in the nature. So, we will go to the concept of, we will now introduce the concept of combined cycle. What is the combined cycle and why we should have combined cycle? So, basically we have discussed the cycle for steam power plant, that is Rankine cycle. We have discussed the cycle for gas turbine power plant, which is Brayton cycle, and both these cycles we have discussed as if they are standalone cycle. Basically, they are standalone cycle. We can have power plant based on either Rankine cycle when the working fluid is a vapor, commonly which is steam, or we can have a power plant where the working substance is a gas and we can have the Brayton cycle. But certain concepts I have already discussed, that for a cycle, let us say this is the thermodynamic plane, a suitable thermodynamic plane. We like to have the maximum temperature of the cycle as high as possible, and we also like to have the minimum temperature of the cycle as low as possible. But minimum temperature of the cycle, there is some sort of a limitation, that atmosphere is the ultimate sink. So, the low temperature, the temperature of the sink, that has to be close to atmospheric temperature. So, let us say this is your sink temperature and this is T atmospheric, and let us say depending on the fuel we are having certain temperature. This is T 1 and let us say this is T 0, this is your source temperature. So, this is your source temperature. Now, what happened that we have to have a cycle between T 1 and T 0. Now, it is not always possible to have a cycle between T 1 and T 0, because the working fluid that has got its own characteristics, and it may not be always possible that we will have a cycle, we can have a cycle from T 1 to T 0. So, what happens? Either one has to have a cycle, let us say from T 1 to some intermediate temperature, let us say we call it T intermediate, or one can have a cycle from some temperature T intermediate to T 0, that is the sink temperature. So, this becomes possible in many cases, that with the working fluid we cannot have a cycle from temperature T 1 to T 0. if we select some kind of a working fluid, we will have a cycle between T1 to Ti, and if we select some other kind of a fluid, we will have a cycle between Ti to T0. We know the Carnot efficiency, which is indicative of the efficiency which a cycle can have, that is T minimum divided by T maximum. So, obviously, when we are having some sort of intermediate temperature, either we are operating between T1 and T intermediate or between T intermediate and T0. So, our Carnot efficiency will be low and the cycle efficiency obviously will be low. So, what could be the remedy? The remedy is that can we use combination of two cycles, then the cycle at the top, which is called topping cycle, I have already introduced this term, will reject certain amount of thermal energy that will be picked up by the cycle at the bottom, which is called the bottoming cycle, and then the combination between these two cycle, thermal interaction between these two cycle is some sort of internal, and we can assume them or we can take them as if they are a single cycle, but obviously they are two cycles. So, that is why this scheme, if energy is converted into work by this kind of a scheme, it is called a combined cycle. The power plants which are operating on this particular scheme, they are called combined cycle power plant. So, combined cycle power plant is very good for better conversion of energy. We can call it, it is very good for energy conservation, and again one way, from one point of view, it is also a very good device for waste heat recovery, because suppose I wanted to have the cycle at the top, that is your topping cycle, then there will be rejection of heat and we can utilize it better by using another bottoming cycle. So, the concept of bottoming cycle, one can think of that it is nothing but a principle of waste heat recovery, and the best way of waste heat recovery, because by this we are producing certain amount of work. So, there are different schemes, propositions and postulations or suggestions for combined cycle power plant. The one of the concept is that one can go for binary vapor power cycle. Sorry, what is a binary vapor power cycle? We have seen vapor power cycle which is which operates on Rankine cycle, when vapor is the working substance of the cycle. Now, instead of one vapor cycle, if we have two vapor cycles, like this has been proposed, that this is our TS diagram. At the top we are having one cycle, and at the bottom we are having another cycle, and the heat rejected by the topping cycle is taken up by the bottoming cycle, and then let us call it Q1, let us call it Q2, and let us say this is your Q3. So, Q1 is heat taken from high temperature source Q2 heat rejected from Q2 from the topping cycle which is picked up by the bottoming cycle and Q3 heat rejected by the bottoming cycle to the ambient. By the bottoming cycle to the ambient. So, you see basically we can think of a, let us use some color, we can think of some sort of a system like this. This system is basically taking heat at a temperature, let us say this is T1 and this is T0. So, T1 is much higher temperature and T0 is the environment temperature. So, basically we are having a cycle between T1 and T0. So, our cycle efficiency will be high. So, this is the concept of your binary vapor power cycle. Already I have told that this is one combined cycle, and two vapor power cycle. The first one or the topping one, people thought probably mercury could be the working substance, and the cycle at the bottom, that could be a cycle where the working fluid is water or steam. So, mercury and water vapor cycle could be a binary vapor power cycle. Even people have thought that there could be three cycles. Basically, then the topmost cycle will operate at the highest temperature, and that cycle could be a liquid metal like sodium, and after that there will be another liquid metal which could be mercury, and the lowest one that could be water or steam. So, this also conceptualized by people, but somehow binary vapor power cycles due to different kind of practical difficulties, it has not become commercially viable, and this is only in the conceptual level. But there are certain possibilities of combined cycle power plant, and there are certain commercial exploitation of combined cycle power plant, very successful commercial exploitation. Those I am going to discuss in the combined cycle power plant. So, if we see here I have written GT plus SPP, that means gas turbine power plant and steam power plant. This is the most successful combined cycle power plant, and all over the world in many places this gas turbine plus steam turbine power plant, they are utilized, and more and more use of this kind of combined cycle power plant we will find in future, because of their high efficiency, high thermal efficiency. So, they are very efficient converter from the thermal energy into work. Then people have also postulated that MHD plus steam power plant, that could be one viable option. MHD is magnetohydrodynamics. Already already there are certain demonstration units, but again there are technical difficulties. So, probably time will only say that whether this kind of power plant we will use in future or not. There are power plants where thermoelectric principle will be used for generating electricity, and this is kind of direct conversion. Directly we will have the electrical energy from the thermal energy without going into the mechanical path, and then bottoming cycle will be your steam power plant. Then there could be thermionic and steam power plant. So, you see MHD, thermoelectric and thermionic, they could be topping cycles, and in the later part of this particular course, the other instructor will elaborate on this. We will not, I will not elaborate now on the MHD or thermoelectric or thermionic. What I will like to do, we would like to spend some time on gas turbine and steam power plant combination, that is one of the successful, very successful combined cycle power plant. This slide you can see a schematic diagram of gas turbine and steam turbine power plant. Obviously, we have shown ideal processes, it is made up of ideal processes, and the basic cycle I have shown here. The ideal cycle, that will be Breton cycle, and the ideal cycle for your steam power plant, that will be your Rankine cycle. So, it is a combined Breton Rankine cycle. Topping cycle is the gas turbine cycle. Already we have discussed the gas turbine cycle. Here the gas turbine cycle will reject heat, ideal cycle rejects heat in a heat exchanger, and in the same heat exchanger that heat will be picked up by water, which will be converted into steam and go to the turbine. So, this is this heat exchanger, intermediate heat exchanger, it is very important for the combination of Breton and Rankine cycle. Okay. In actual case, of course, this cycle will not be a closed cycle. After this heat rejection to the working fluid of the bottoming cycle, which is water or steam, it will go to the stack and ultimately it will be left to the atmosphere. So, the heat exchanger over here, this heat exchanger is called as HRSG or heat recovery steam generator. Heat recovery steam generator. Now, combined cycle power plant, of course, from the thermodynamic argument I have told that it will have a higher efficiency, but let us see how it can have a higher efficiency. Let us do some sort of a small analysis how it can have a higher efficiency. Let us try to see. So, let us say this is the topmost reservoir at the highest temperature T 1, then we are having some sort of heat engine. This is taking Q 1 amount of heat and this is doing W 1 amount of work, rejecting Q 2 amount of heat to some thermal reservoir which is at temperature T 2. From the same thermal reservoir, Q 2 amount of heat is taken by another heat engine and it is doing W 2 amount of work, and then ultimately it is rejecting Q 3 amount of heat to another reservoir which is at T 3. So, one can write T 1 that is greater than T 2 that is greater than T 3. Okay. And total work done that is equal to W, that is nothing but W 1 plus W 2, that is the total work done. So, efficiency of this cycle, now what we can do, the combined cycle can be taken like this, which can be thought as a single cycle, which is taking Q 1 amount of heat and rejecting Q 3 amount of heat, while doing W 1 plus W 2 amount of work. So, for this combined cycle, what will be the efficiency? So, the efficiency of the combined cycle will be eta combined, that is equal to again W by Q 1, that is the thermal energy we are taking, and that is equal to W 1 plus W 2 divided by Q 1. So, what one can write, this is equal to W 1 by Q 1 plus W 2 by Q 1. W 1 by Q 1 is nothing but the efficiency of the first cycle or topping cycle, that is equal to eta 1 plus W 2 by Q 1. W 2 that is equal to W 2 is equal to Q 2 minus Q 3. Q 2 again one can write Q 2 is equal to Q 1 minus W, that is Q 1 minus eta into Q 1. So, that is Q 1 minus Q 1 within bracket 1 minus eta 1. So, Q 2 is equal to Q 1 minus W. that is q 1 minus eta 1 q 1 and that is q 1 within bracket 1 minus multiplied by 1 minus eta 1. So, that is equal to your W 2 q 1 minus q 1 into 1 minus eta 1. So, W 2 that is equal to q 1 1 minus eta 1 minus q 3 and what is q 3? Q 3 we can write q 2 minus W 2. Q 3 is equal to q 2 minus W 2, that is q 2 minus eta 2 into q 2 and this is equal to q 2 1 minus eta 2. So, this is what we can write. Then ultimately we can write W 2 is equal to q 1 1 minus eta 1 minus q 2 1 minus eta 2 and q 2 we can write again replaced by your q 1 1 minus eta 1. So, then we have got the expression of W 2 in terms of q 1 we have got. So, let us go back to our previous this one derivation. Eta combined is equal to eta 1 plus W 2 by q 1. So, this is eta 1 plus q 1 1 minus eta 1 minus q 1 1 minus eta 1 into 1 minus eta 2 divided by q 1. So, it will be eta 1 plus 1 minus eta 1 minus 1 minus eta 1 into 1 minus eta 2. So, obviously, it will be 1 minus So, if there is no heat loss in between, then the combined cycle efficiency will be given by this expression. This is an important expression. I can write eta combined over here. This is an important expression. It gives the higher limit of the efficiency of the combined cycle when the efficiency of the individual cycles are known. In actual practice, we will not be able to achieve this high efficiency, because whenever heat will be supplied from the topping cycle to the bottoming cycle, there will be some amount of heat loss. So, the efficiency of the combined cycle will be lower than this ideal case, the efficiency which I have derived just now. So, from here we will take up and see the certain attributes of the combined cycle power plant in our coming lectures. Today we like to close here. Thank you.